The last thing we left off on was freezing point depression. I believe you're the one that piped up and said, I got that. And we know that, excuse me, colligative properties of solutions allow us to change the boiling point and the freezing point, to make the freezing point lower so that it has to be colder for it to freeze, or else make the boiling point higher so that it has to take a higher temperature for it to boil. We did a calculation. It's really easy in terms of delta T. Delta TF equals M and then some sort of constant. The little m stands for molality, which is moles of solute per kilograms of solvent. And the delta T stands for the change in the temperature. Remember, not the actual temperature, but the change in it. So if you calculate that, and it's a freezing point, realize you've got to subtract that from the original freezing point. If you calculate a change in temperature that's for a boiling point, you've got to add that to the normal boiling point. So you're going in opposite directions. So let's take a look at this. We know that we can elevate the boiling point of something by dissolving something in that solvent. Okay? So again, it's going to be directly proportional to how concentrated that solution is. If you take a look at that equation, if you know that, well, let's get to it. This equation here, obviously, the change in the boiling point temperature is going to keep going up. This doesn't change. So if that keeps going up in higher concentration, then that's going to change even more. So that's why it's directly proportional. Okay? Now remember that if you're going to calculate a problem using boiling, or to determine boiling point elevation, make sure that you use Kb, not Kf, for those values, because there's a different one. There's one for freezing and one for boiling for every solvent. Okay, so we have an ethylene glycol solution just like we had last time. We have an ethylene glycol solution just like we did last time, except this time, instead of calculating the freezing point, we're going to go for the boiling point. Same concentration even. So there's our concentration. The equation that we need is this. Now you can do all this if you want, or you can just realize in your head what I said, that if you calculate delta T, you just have to add it to the boiling point. Okay? So plug in your molality, which is going to be 1.7 molar. Skip that slide. There we go. Molality is 1.7 moles of solute per kilograms of solvent. If you look up for water, because this is an ethylene glycol solution, it's actually water-based. Like if you ever make your own antifreeze, you know that you got to mix some of it with water. Whenever you can buy it pre-mixed sometimes. But so put the Kb in for water for the boiling point. Multiply those together, you get 0.87 degrees. Now that's not a big change. So instead of being 100 degrees Celsius for its boiling point, it will be 100.87 degrees Celsius. And then if you continue to increase this, you could change this even more. So you could see that with the same concentration of ethylene glycol, we affected the freezing point more than we did the boiling point. The freezing point dropped by a few degrees, if I remember right. It went down about to -3 or so. Here it only went up not even 1 degree. So you're going to have more of an impact on the freezing point than you will the boiling point, but you can have an impact on both. All right. Something interesting here. If you've already grasped this in your other classes, then that's fine. But if not, here's a good chance to actually try to understand this. We mention osmosis all the time. Osmosis and diffusion. Diffusion's an easy concept to understand. Things are going to move from where there's a lot of them, by randomly bouncing around, end up spreading out to where there's less of them. Okay? So what's the difference in between diffusion and osmosis? Well, osmosis is pretty much the diffusion of water, but it's set up in a certain way. Let me show you what I mean. Instead of just, let me try to describe it in pictures if I have one. Let me go back then. Hang on a minute. Let me show you this. Imagine this. I can't draw. This is supposed to be a glass tube that's shaped like a horseshoe. It's a little fatter on one end, but that's okay. Now, let's say that I've got a glass tube that is divided right here. There's a barrier between both sides. Okay? That means the contents from this side can't get to the contents of that side, vice versa. Now, let's say that I put in here this amount of solution on both sides, and that is equal. All right? I'm going to fill this side up with a solution. I'm going to fill this side up with something, and I'm going to make sure that the volume is exactly the same on both sides. Now, the difference is, on this side, I'm going to have pure water, distilled H2O. On this side over here, I'm going to have salt water. Okay? Now, that's H, not A. I've set up a situation. If diffusion were allowed to happen, and things normally would move just where they wanted to move to, where would the water want to move? From left to right or right to left? From left to right. That's right. What about the salt? Where would it want to move? It would want to move from right to left. All right. What if I did this? Whoa. Too big. What if I created a situation where I put a semi-permeable membrane, a membrane with tiny little chemicals maybe, or tiny little holes, whatever, something that allowed water to go through, but not salt ions. Okay? So water could move, but salt could not. But what we've got to realize is that there is still a potential here. Salt still wants to go that way, even though it may be physically prevented from squeezing through here and getting there. Water still wants to come this way, and it can. So as soon as I pull up this and insert a semi-permeable membrane instead of just a dividing line, when that becomes sort of permeable, at least to water, what will happen to the contents of this tube? What will you see happen? This side's going to go up. Okay? Water's going to go ahead and diffuse, and it's going to continue to diffuse until the concentrations of water try to balance each other out on both sides. All the while, sodium chloride couldn't go anywhere. Okay, sodium chloride's a bad example because it's really small. I could have picked like a big sugar molecule. That would have been better. But whatever the solute is, it doesn't matter. It's trapped over here because it cannot get out. And when you have a situation like this where you have a boundary and you have concentration differences on either side of that boundary, and water moves because of the solute being trapped on one side, that's osmosis. Okay, that's what osmosis does. Now, in real life, we think of this as a cell. If this was the inside of the cell, and this was your cell membrane wrapped around the outside, which is semi-permeable, it can control what comes in and out. If this is your cell membrane and this is the external environment, what would happen to this cell? Well, if you have stuff dissolved in your cell, and you drop your cell in pure water, what will happen to it? It'll take in water, right? Because of what we just said right here. There's more stuff over here. If there's a higher concentration of water on the outside than there is the inside, water's going to want to come in. And water can freely move across the membrane of our cell. It comes in and out very easily. Other things are trapped inside. Big protein molecules, other large organic molecules. They don't just get to freely float across our membrane. We have to control it. That's how we stay alive. Okay? So, this whole movement like this, set apart from a membrane, is osmosis. Now, that's the summary for all of that. Pressure, osmotic pressure. If you go back, it's like I lost my drawing. If we have this same drawing, and we know that the water level is rising on this side because of the dissolved solute, and it dropped on this side, if we had a piston right here that we could push down on top of and force that water back down and push it through back to where it started, whatever pressure would be necessary to keep osmosis from happening, to force down on it to make it stay equal even though it wants to move that way, that's called the osmotic pressure. Okay? That's the osmotic pressure of a solution. So osmotic pressure obviously is very much related to concentration, right? Because the higher the concentration of the solute over here, the more water is going to want to move this way. And the more water moves this way, the more pressure it's going to take to oppose water moving that way. Okay? All right. And this is where you see these words, by the way, in your biology classes. Isotonic, hypotonic, hypertonic. Tonic is in reference to the pressure, the osmotic pressure of the situation. In an isotonic situation, the osmotic flow gradient is the same on the inside and the outside of, like, the cell, for example. Okay? In a hypotonic, and one way to think about this, if you're trying to remember it, if you ever have to remember it for something, hypo swells up like a hippo. Okay? If you have a hypotonic solution and you put a cell in a hypotonic solution, what that means is you would have a cell. Here's a jar of solution. Hypotonic means there's very little solute out here compared to what you have inside the cell. Hypotonic means low, right? Hypotonic means there's a very low amount of solute on the outside compared to the inside. If that's true, that means there's a higher concentration, higher percentage of water out here and a lower percentage of water in here. These X's aren't water. These X's are the things that are dissolved in water. Okay? So if you have a lot more dissolved in the water inside the cell, you're going to have a lot less water, percentage-wise, compared to what's going on out here. So which way do you think the water wants to move in this situation? In the cell or out of the cell? Into the cell. Into the cell, because we've got, like I said, notice I say here, this low percentage, you can't see it very well, but the low percentage is in reference to water. There's a less concentration of water in here because there's more solute. Okay? So more of that space is taken up by solute as opposed to water molecules. Out here, look how much free reign you've got of water molecules, right? You've got a lot more concentration of water out here and a lot lower concentration of solute. So which way is the water going to go from high to low? There's a higher percentage of water out here than there is in here, so water wants to go in, and that cell can swell up, okay, in a hypotonic environment. Another way to think about this is that wherever the salt is, like in the human body, one of the things about blood pressure is you have to decrease your sodium intake. I'll show you why here in a second with the next picture. But the point is salt, generally, water goes wherever the salt goes. So if I have a lot of salt, for example, in here, it sort of acts like a sponge and draws water towards it. Now, it's not a chemical reaction. It's not sponging up the water and soaking it up. It's just setting up an osmotic gradient. It sets up a situation where there's a lower concentration of water in here, a higher concentration of water out here, so it flows in. That's why you don't want to salt your meat, before you cook it. If you take a piece of meat and dump a bunch of salt on it, there's natural juices, right, in the cells of that meat. And what you will do is, as it cooks, some of that water is released, and then once you start creating a saltwater solution on top of that, you've created an osmotic environment now where water, there's a higher concentration of salt on the outside water, on the outside of the cells. There's a lower concentration of salt on the inside of the cells now compared to what you've dumped on there. So water gets drawn out. It flows, there's a higher percentage of water on the inside of the cells, lower percentage on the outside because you put more salt on it, and that water moves from the inside of the cells outward and dries out that meat. Okay? That's why you can salt cure things too. You remove the water content from them by salting it excessively. All right, another thing is when you're out on the ocean, as we all go, and we're just trying to play Survivor for the fun of it by ourselves, and we're in a raft and we get really thirsty, you don't dip your cup down in the ocean and take a big swig of water. Bad idea. Not only does it taste like crap, it could kill you. Not just because of the things floating in it either. Because salt water, if you put it in your body, think about what you're doing. Okay? Say you drink a bunch of salt water. Notice here you've got in your colon, you've got a bunch of, which is mostly responsible for the water absorption, pulling it out after digestion, that kind of stuff. Notice that you've got water molecules and you've got salt molecules, salt ions dissolved in it. Okay? Now, in your bodily tissues, we work through homeostasis to maintain a certain concentration of certain dissolved solutes and water and things like that. So if you ingest salt water or a 3% sodium chloride solution and put a high amount of sodium chloride inside, what you do is you can compare both sides of this using this as your membrane, the colon wall. You can look and see that there is a higher concentration now, percentage-wise, of water out here. Just look at the molecules. Look at the pictures that are present. Okay? By putting more salt in here, you can see visibly that there is more salt in here than there is out here. And if that's so, that means more of this space in here is taken up by salt and less of that space is taken by water. Whereas more out here, very, very little of the space is taken up by salt, much more of it's taken up by water. So which way does water want to flow? It want to flow from where there's a bunch of it to where there's less of it, right? So what's going to happen is all this water is going to come inside. There's two big things we got. Well, one big thing. The first thing that's going to happen is going to lead to the problem. Massive diarrhea, first of all, because all this stuff's going to come rushing in. It's going to water down the contents of the colon, and it's going to get flushed out. Okay? What happens to our body, of course, is dehydration once that happens. So you actually worked exactly against what you were trying to prevent by drinking all that water. If you drink a bunch of salt water, you're going to end up dehydrating yourself even worse. This was on an episode of CSI. Somebody killed somebody like that. Yeah. Okay, so anyways. This is the explanation of osmosis that I already talked about. Much better drawing this time. But you can see that if I have some kind of dissolved solute in the water over here and I just have water right here, look what wants to happen. There's equal amounts on both sides in terms of volume, but more of that volume is comprised of water on the right side, less of it's comprised of water on the left side. So water wants to move across. Okay? Now, those blue dots, the solute would want to move towards the right, but they can't. They're physically prevented from doing so. Okay? So what will happen then is this net effect, more water will move this way. That water level will rise until it rises to the point where it is stopped. And then whatever column is standing of water right there that exerting the pressure, that's the osmotic pressure. That's what's stopping osmosis at that point. And then, of course, in blood cells, you guys will see all this kind of stuff. But a normal red blood cell in an isotonic solution, when it gets in a hypotonic solution, it can swell up. If there's too little solute on the outside, what will happen is more water will be sucked in towards the inside of the cell. With cells that are in a hypertonic solution, then there's going to be more salt on the outside of the cell, and as a result, it's going to draw that water out of the cell through osmosis, and it's going to shrivel up.